Good morning and welcome everyone to this year's Bolin Science Seminar. My name is Nina Kirchner. I'm one of the two directors of the Bolin Center, and it's my pleasure to host today's lecture given by Professor Roberto Buizza from Pisa in Italy. But Roberto will actually be connecting from London in just a few minutes, and I'll introduce him also just in a second. The Bolin Center is named after Professor Bert Bolin. He was a professor of meteorology here at Stockholm University, and he was also the founder of the IPCC, who was awarded the Nobel Peace Prize in 2007, right before Bert Bolin sadly passed away. And in honor of Bert Bolin, from the year 2008, a distinguished Bert Bolin lecturer is invited to Stockholm University every year to hold a popular science lecture. This is today at 1 o'clock for a wider audience, and also to give a more specialized science seminar. This is what we are having now, and this is for a more specialized audience. And usually we would all gather here at Stockholm University, but today we do it using a Zoom webinar instead, and I need to say a few words about the practicalities. So the full functionality of this webinar will only be available to you if you have downloaded and installed Zoom. And the full functionality becomes relevant when we come to the questions after Roberto has given his talk. So if you just run it in a browser, you will not be able to use the full functionality, but we will repeat it after the talk. So to ask a question, you can use the question and answer chat, or you can raise your hand. And then our team behind the curtains will give you voice and audio to give you possibilities to raise your questions. So, but now after these practicalities, it's time to introduce Professor Roberto Buizza, this year's Bolin climate lecturer. Roberto, you're from Italy, where you also started your university education. You have a physics degree from Milano, but your education brought you also to London, where you got degrees in mathematics and business administration. You joined the ECMWF, that's the European Centre for Medium Range Weather Forecast in Reading in 1991, and you have been lead scientist and head of the predictability division there in many years, actually more than 20 years. You're an expert in numerical weather prediction and how to bridge the gap between weather and climate. Roberto, you're also an expert on ensemble methods, where you focused on defining optimal ways to simulate initial and model uncertainties, and you're a developer and key promoter of the use of coupled models for weather prediction. And in 2018, you returned back to Italy. You joined the Scuola Superiore Sant'Anna in Pisa, where you now hold a full professorship in physics, and where you, together with colleagues in Pavia, are establishing a new inter-university center to study climate change and its impacts, and where you also identify sustainable action. So we are honored to have you with us, Professor Roberto Buizza, and we look forward to your science talk with the title Uncertainties, Estimation in Weather and Climate. Thank you so much, and we're looking forward to it.
Thank you very much, Nina. I hope you are all hearing me well. I'm now going to go to full screen to share my screen, but before I do that, let me thank a lot the Bolin Center for the honor that they gave me by inviting me to give a science seminar and the climate lecture later on. Right, I guess now you should be able to see my screen. If not, please let me know. So the title of my science seminar is Uncertainty Estimation in Weather and Climate. So what I would like to do in the next 40 minutes or so is to go through the following four main topics. The first point I want to make is why we need to estimate uncertainty. Second point is that we could do it with reliable ensemble, and I will stress the word reliable. Third point is that I want to discuss and give you a brief overview of how we have built reliable ensembles, and then a couple of comments on how I think we can further progress in understanding weather and science and climate, and how we could design systems which are even more accurate and more reliable. So why do we need ensembles? Well, an example comes from the prediction of extreme events. I'm just showing here an image from Hurricane Sandy. Hurricane Sandy hit the United States in 2000, and about 10 days beforehand, there was a lot of discussion between us when I was still at the European Center and colleagues in the US, whether this hurricane was forming would actually reach the coast and possibly hit New York. Now, we had at our disposal a couple of forecasts. For example, on the left, the dotted line that you see is the forecast from what was the European Center High Resolution Model. This is a system that takes about 10 times more CPU than the one I will describe later, which is the ensemble system. So as you can see, 10 days before, on 23rd of October, a high resolution forecast from the European Center was suggesting that the hurricane would stay over sea, as most of the times hurricanes do. On the right, you see an alternative track. This track was generated using a lower resolution system. As you can see, this one is turning left. And indeed, with a red line, I'm showing the track that was actually followed by the Hurricane Sandy, essentially by connecting the crosses that you have seen in the previous pictures. So here is a clear example that if you have at your, if you have information coming from a single forecast only, if you have a single information about what's going to be the most likely scenario of a system in the future, it's going to be hard, first of all, you might be wrong, and secondly, it's going to be hard to understand whether there is any chance that your single forecast is going to be right or wrong. Clearly, if instead of having one forecast only, you had at your you had access to a probabilistic forecast where you can see a range of possible scenario of possible tracks that the hurricane would do, we could use them to estimate the accuracy of your forecast, to estimate the forecast scale, to give you an index of confidence. What you see here is the probability, the strike probability computed from the European Center ensemble. At that time, I will describe the ensemble later on. My point here is simply that you have much more information and much more complete information if you have access to a probabilistic forecast that allow you to estimate how certain or uncertain you are about the track of or about the future state of a system. In this case, as you can see, the spread, the divergence of the tracks is small up to 6-7 days ahead, and then there is a lot of uncertainty with tracks, some of the tracks staying overseas, some of the tracks actually going into land and possibly hitting New York, as actually happened. Second example comes from the terrible situation that Australia experienced last November, December, and January of this year, when they were hit by extreme weather condition, extreme heat, extreme wind, drought, and this led to terrible fires. So again, what you would like to be able to do is to estimate, possibly months ahead, whether there is any chance that the weather in what is the Australian summer would actually favor the development of a situation like that. So one of the drivers of a weather condition in Australia in their summer is actually what's happening in the Indian Ocean. The so-called Indian Ocean dipole, which is a large-scale pattern of Indian Ocean, is actually has been linked to weather conditions in Australia later on. So when you are in a positive IOD, what you have is that you have a decrease warm, moist air hitting the continent, decrease rainfall in Australia, and this can lead in the months afterwards to actually drought and possibly fire. So the question I want to ask is again, would we have been able to predict that this was the case in June 2019, when we were issuing the forecast in June 2019, or not? So I mark here a value of the IOD of 1.5, so an SST anomaly of 1.5 degree and the question that I want to ask is whether there is an anomaly larger than 1.5. So if you had only one forecast, again, what you see in June 19 compared to June 18 is that, yes, the temperature on average is of a SST is higher. It's about 1 degree warmer than the year before, but you cannot say whether in the future, so in September, October, November, you might have conditions, anomalies higher than 1.5 degree. A different story would be if you had access to an ensemble of forecasts. What I'm showing here are quartiles, predictions from the European Center Seasonal System 5, the minimum and maximum SST anomaly, the 25th and the 75th percentile in dashed, and the ensemble mean in solid. So if you look at 2018, there was here also a large spread in October, but with a very small indication, very small probability that anomalies would be above 1.5 degrees in September and October, leading to conditions in November and in December in Australia. While if you look at 2019, there are almost 50% of the ensemble members giving an indication of warmer conditions. And indeed, in red, you see what has been happening. So very warm conditions in the SST as predicted by the ensemble. Even better, if you had access to not only a forecast PDF, which is what I just showed, which is this pink box and whisker diagram. Better would have been if you had access also to the model climatology, which is this green box and whisker, and the observe anomaly, which is the yellow and orange shading. So the point I want to make is that if you have access to a range of information that allow you to estimate probabilities of events to occur in a climatological sense, in the model climatological sense, and in your most recent forecast, you would have much more information than if you had access to a single forecast only. Going even farther than seasonal to decadal prediction on the left and seasonal projection to the right, the story is similar. Again, if you it wouldn't make sense to do decadal forecast like what you see here on the left from the Met Office, or seasonal projection, what you see here from IPCC, if you did it with a single forecast only, with a single time integration only. Okay, best would be if you actually had access to a whole range of forecasts. I've seen that some of you raised your hand. If you don't mind, I will go through my seminar and then I will take questions. So that was my point number one. We need to estimate uncertainties. And as you have seen from some of my diagrams, we could do it with a reliable ensemble, okay? What is an ensemble prediction system? Well, it's a way to generate forecast probability by estimating the initial state of a system, initial PDF of a system, and propagating it in time using a small number of time integrations. In this way, you can estimate how the forecast probability will look like. But ensembles are not the only way we could use to make probabilistic forecast. Indeed, in the 1990s, when people started developing ensemble systems, there was some work done, for example, by Martin Ehrendorfer, which I'm mentioning here, to try to see whether one could use more sophisticated and actually more correct, from a theoretical point of view, approaches to estimate the PDF of forecast states. Best way to do it is to integrate the so-called Liouville equation, which is the continuity equation for a PDF of a state vector xt. Okay. Problem is that this equation is inhomogeneous, quasi-linear, and integrating it in time to find solution is extremely, extremely expensive, especially if we take systems with a number of degrees of freedom as the weather or the climate. Martin Ehrendorfer did a fantastic job when he tried it with a three-dimensional system, and he actually did some simulations and showed that you actually would do much better when using ensemble if you were able to fully integrate the Liouville equation. But at the same time, when he thought about the possibility of using the Liouville equation and integrating it for a high-dimensional system, he clearly stated in his work that the high dimensionality of a phase space encounter in the case of realistic meteorological models seems to prohibit this approach. Indeed, this is still the case, even 25 years after that work, even with computers which are 10 to the third more powerful than at that time. So the only way we can really do it is using ensembles. But what we need to be careful is that if we want to really use the information coming out from ensembles, ensembles must be reliable. What do I mean with a reliable ensemble? I mean that if the ensemble spread spanned by its ensemble members is small, so here what you see is some ensemble members in blue, the ensemble mean in green, the actual trajectory, it's a schematic of a true state of a system in red. So in a reliable ensemble, reality behaves as one of the ensemble members. If this is the case on average, in an average sense clearly, what you could do is use the spread of the ensemble, so the divergence of the average divergence of the members, for example, from the ensemble mean, as an indicator of, as a predictor of the error of the ensemble mean. So in a reliable ensemble, when the spread is small, you should expect the error of your prediction to be small. By contrast, when the divergence is large, you cannot say much about where reality is. It might be close or it might be far from your most likely scenario, or even if you compute probabilities, you might be not very accurate in your prediction. And a way to measure whether the ensemble you have built is reliable is to use the so-called reliability diagram, which maps forecast probabilities versus observed relative frequencies. A reliable ensemble would have dots for different probability values, 10%, 20, 50, and so on, corresponding to observed frequencies. So if you predict an event with a probability of, say, 75%, you would expect it to occur 75% of the times. This clearly is has to be verified in over many cases. And you have perfect reliability when your couples forecast probability versus observed relative frequency lie on the diagonal. The Brier score and the Brier-Ski scores are metrics that you could use to assess how close you are to this diagram. Okay, so how do the ensembles that we have built look like? Well, these are some plots from the European Center. This is, for example, the reliability diagram for the prediction of temperature, 2-meter temperature anomalies over Europe, 4 days ahead and 10 days ahead. You see 4 curves in each panel. They correspond to temperature anomalies of more than 8 degrees, more than 4 degrees in orange, less than 4 degrees in green, and less than 8 degrees in blue. So what you see is that at 4 days, they are quite close to the diagonal, so not too bad, actually. You go to 10-day forecast, and you start seeing that for some of the variables, the curves start moving away from the diagonal, indicating that the system is becoming less reliable. In this case, is linked to the fact that the system has a cold bias. Now, as I said, this verification must be done over a large number of cases. In this case, the verification was done between the 1st of January and the 31st of March of 2020. So it's a very recent verification that you can find on the European Center website. So not too bad. These are grid point predictions of 2-meter temperature anomalies. What if we go and look further into the future? So how do, for example, look monthly ensemble forecasts? Are they reliable or not? Can we trust them in giving us valuable information of events that could happen over the time scales? Again, here I'm showing one example from your European Center monthly ensemble. Again, one of the best, if not the best in the world. What you see is a reliability diagram of ensemble forecast of weekly mean temperature between day 5 and 11, 2-meter temperature. And again, you can see that the curve is very close to the diagonal. And indeed, if you look at forecasts valid for 2, 3, 4 weeks ahead, you can see that forecasts are reliable up to 25 days ahead. Even further, we can look at the seasonal time scales. Again, I'm looking at near surface temperature anomaly. In this case, it's verified over land and sea points against the analyses. These are forecasts issued in May and valid for months 2 to 4. So forecast valid for June, July, and August. And again, you can see that 3 months averages of 2-meter temperature anomalies actually are not too bad. They are quite reliable. They lie between these 2 curves of a reliability diagram, which are the curves of that indicate the area where you have skillful forecasts or forecasts which are better than climatology, than a climatological forecast based on the statistics on past events. If we go and look even further into decadal, how reliable are these forecasts? Well, this is work from Susanna Corti, Antje Weisheimer, and colleagues who looked at the reliability and the skill of decadal forecast. Unfortunately, when you go into the longer time range, you have access to fewer events. So it's not so easy to assess reliability when you go into the longer time range, because you have a smaller number of independent events. So here, Susanna and Antje look at 2 to 5 year averages of 2-meter temperature over Europe, 6 to 9 year averages, and 6 to 9 year averages. And what they reported is that, yes, there is a reliability in the forecast. So the forecasts are able to discriminate between low frequency and high frequency of events. Then they actually investigated whether what you get out of a decadal forecast is essentially a signal of climate change, of a warming. So they trended the land data. So this is all verified against land data only. So what they did is to remove the climate change signal from the forecast, and still they could see that at least for Europe, the forecast valid for year 2 to year 5, there are reliable information in the ensemble of forecast. Okay, this is not the case for all the areas they look at, but for some regions they reported that this ensemble was reliable and skillful with the Brier skill score, which is positive. So let's recap where we are. We said that we want to estimate uncertainty. We said that to do it, we could use ensemble, and we said that we need reliable ensemble. So if we look at the medium range and the subseasonal, usually centers like the European Center, Met Office, Météo France, or NOAA, the centers were engaged and provide users with operational forecast, look and assess the reliability and the skill of this ensemble forecast over 20 plus years, okay? And results usually show that they are very good, they have a very good reliability and skill for synoptic scales and upper area variables, and for monthly also good reliability and skill for, say, large scale, low frequency phenomena. There is clearly a dependency of the skill and reliability on the phenomena scales. So the forecast skill horizon is not the same for all scales. The fast and local scales can be predicted only a few days ahead. The slow and large scales, like the weekly averages, anomalies of a big region, could be predicted skillfully up to weeks or months ahead. Seasonal ensembles, again, also usually reliability and skill is assessed over very many cases, like 20 to 35 years, depending on the center. And again, usually, so the different groups report good reliability and skill for very large scale and low frequency phenomena. I'm talking here about El Nino, for example, or very large scale anomalies of the scale of a continent. So clearly you cannot expect and ask reliability and skill for grid point values over a seasonal time range. But decadal, as I said, there are very few work who look at the reliability of decadal forecast. Corti, Weissheimer, and colleagues did one of them. Usually the problem is that you have only access to very few independent decades that you can verify on. So they looked at, for example, 10 independent 4-year forecast. And they reported that there is good reliability for 4-year averages on some regions. This talk is also about uncertainty in climate. So what about reliability in climate projections? Has it been assessed? Could it be assessed? This is clearly a big problem, and we will come back to it maybe later on, because clearly the problem with long climate projections is that we have access to very few decades, or say 20, 30-year periods where we can verify how our system behaves. So third point, how did we build this reliable ensemble? I will answer to this question mainly looking at what happened at the European Center, which has been the leaders in this field for many years and is still. So in weather, let me just state that what I think you would all agree, weather prediction is an initial value problem, and with this I mean that a forecast state is essentially computed by integrating the model equations in time, knowing initial condition of a system. Okay, so if you think about how we do weather forecast, it's clear from this very simple schematic equation that you could have errors in the forecast due to errors in initial conditions, and this could come from observations, from errors in the observations, or the fact that the world is observed differently in different areas or in different for the different components, or you can have errors coming from model imperfections. Okay. While if we think about the climate program, the climate projection are very much dependent also on what is called the representative concentration pathway scenario. So the assumptions you made on how the future concentration, for example, of greenhouse gases, the population, the energy needs will actually develop. Okay, so in the climate projection, you also need to make some assumptions about your climate forcing scenario if you really want to estimate the uncertainty. And indeed, for example, as shown by work by Sutton and Hawkins and reported in the IPCC, if you look at the uncertainty in global decadal mean temperature, you see that most of the signal after the first 10 years or so comes from this RCP and the uncertainty in the RCPs. So let's look at the medium, monthly, and seasonal time scales. How did we build reliable ensemble? Well, when in 1992, beginning of the 1990s, when different groups started designing ensembles, the question was, okay, what is more relevant? Is it more relevant to estimate initial condition uncertainties or model uncertainties or both? Clearly at the time, all was, first of all, it was not clear whether ensembles could work, whether we could build reliable and skillful ensembles. So at that time, the two leading groups, the groups at the European Center, the NCEP, focused mainly on initial uncertainty estimation. Why was that? Well, because experiments showed that if you compare forecasts run with different models from different initial conditions, the differences were coming mainly from initial condition difference, at least in the first 5 days. And this is an example of this work. It's from Harrison et al., 1999. What you see here at the top is the difference between UK forecast run from UK initial condition, the EC forecast from EC initial conditions. So what we did at the time with the team of Met Office, we explored whether the differences were coming mainly from using a different model in the integration or starting from a different initial conditions. So here at the bottom, you see the difference of, in this case, the UK forecast and the EC forecast starting from the same initial condition from UK Met Office. As you can see, it's rather small compared to the difference in the forecast. We're looking at 5-day forecast of geopotential height at 500. On the right, top right, you see the difference of two forecasts starting from different initial conditions, EC and UK, run with the same model, ECMWF. And here you see that the shading, the values that we reach in the divergence of these two forecasts is comparable to the difference between the two forecasts, and is comparable actually to the mean error of the two forecasts. Now, if you look at this paper discusses different cases, some statistics are reported, but essentially what we knew is that indeed initial condition errors were dominant in the first 5 days. After that, clearly model errors were starting to be important as initial condition error. But since we were trying to develop systems that could be used mainly in the medium range, so first week of forecast, we focus, NCEP and ECMWF focus more initially in the estimation of initial uncertainties. So how did we do it? So at the European Center, we followed the strategy based on singular vectors. The idea was that we wanted to compute patterns, perturbations in the atmosphere that would have the fastest growth in over a finite time interval. Okay, we computed them by solving an eigenvalue problem. Eigenvalue problem defined by energy norms and linear and adjoint propagators. Why did we choose this? Because we thought, well, if we can only run a small number of ensembles, we better try to design them so that they can explore directions along which errors could grow fastest. At NCEP, they followed a similar approach, but they used a different method, so-called breeding method. Essentially, the main idea behind these two approaches was similar, was what I would call a reduced sampling approach. We cannot explore all directions of a phase space of a system. We cannot run very large ensemble members, so we better prioritize and try to identify the very few directions that could explain most of the forecast error. So we did it with singular vectors, and NCEP did it with Brier breeding cycle. Canada would develop a system later on and put it in operation in 1995. Actually, they followed a different approach, a full Monte Carlo approach. Well, they decided from the beginning to sample all sources of forecast error, perturb input variables, perturb observation, and perturb model parameters. Then we, later on in the 1990s, clearly it was clear, people started realizing that we needed to take into account also model uncertainties. And Canada actually showed to the world that if you introduce also perturbation in the model, you could improve the divergence of a system, make your ensemble more reliable. At the European Center, we introduced a new approach to simulate model error, so-called stochastic methods, where we introduced perturbations in our integrations, which were based on stochastic noise. Okay, and the noise was designed to simulate errors happening on 3 different time scales, on a fast and small time scales, on a medium time scales over 3 days, and over a longer time scales. In this way, what we try to do is to simulate errors due to different processes. For example, if you think about the long time scales error due to SST drifts or drifts in soil moisture. On the 3-day time scales errors due to, for example, problems of a model to simulate large scale patterns like blocking or consistent flows, while the fast scale was supposed to simulate errors due to the physical processes themselves, for example, convection. We get to now 2005, when the 3 groups who were running operational ensemble decided to compare their performance, try to understand where we were and whether we could learn from each other. And this is a graph from one of the papers we wrote all together, published in the monthly weather review. Again, what we saw is that we were not terribly good. So there was still some under dispersion in the at the end of the forecast, and NCEP and Canada had to start with very large initial perturbation to be able to have enough spread in the medium range. So clearly, the way we were designing the system was still not very accurate. We were missing something. We were missing something in the early range. We were missing simulation of model uncertainty in the later range. So this is a different way of looking at reliability by comparing the average error of the ensemble mean, the solid curves, versus the average spread of ensembles. As I said before, the two should be as close as possible, if not identical. And even with the ECMWF system, which is the green one, which has the 2 curves closer to each other, there is still a little bit of overestimation in the early range and underestimate shown in the later range. So more work was put in the second decades of, in the second part of the 2000s to actually keep improving the system. The European Center went back to thinking about the way the initial perturbations were designed. There was some work done by Ian Bachmeyer while at the center on trying to constrain these singular vectors to know more about the initial uncertainty. How this was done by trying to use the Hessian of a data simulation cost function as an initial time norm. So substitute the energy norm at initial time with the square root of a Hessian of a cost function. Okay, what was found at that time is that okay, we could compute the single vector, we got very interesting results, but the computation was very expensive and the impact on the forecast was not very large. So at that time it was decided not to follow that route, but something else was tried. So again, thinking about the example of a Canadian ensemble, we decided to try to design an ensemble of data simulations where we would perturb the observations to estimate the initial state of a system and get a so-called ensemble of initial state. So each of these analyses was generated by running a 4D var over the same time window as the operational analysis, perturbing the ops, perturbing the model to get a reliable estimate of the analysis uncertainty. And what we did was to add to our singular vector-based perturbation a new set of perturbation computed using the EDA. The structure, the scales, the growth rate of the perturbations were quite different. If you compare singular vectors here at the top and EDA-based perturbation, singular vectors were much more localized, were growing much faster, were essentially concentrated on the synoptic scales, while EDA-based perturbation were spanning also the smaller scales, and we were less localized, and we were clearly sensitive to analysis error or observation error. Furthermore, some work was done on trying to improve the model uncertainty estimation. Work by Glenn Schatz at the Met Office. Glenn then joined the center and worked a few years at the center, showed that it's very important to simulate the effect of unresolved scales on the resolved scales of a model. So this diagram, adapted from Brian Hoskin's paper of 2012, shows essentially what we do with the numerical model prediction. So we're trying to predict phenomena at a certain scale by simulating as accurately as we can the external forcing, the wider long-range scales, and clearly the shorter scales, no? Where the atmosphere doesn't have a break in the energy spectrum. So if you want to predict a phenomena with a certain spatial and temporal scales, you need really to take into account the larger and the smaller scales. Problem is that our models have a certain resolution, okay? And so models usually are not capable to simulate, or they try to parameterize the effect of the unresolved scales on the shorter scales, but they're usually lacking this type of interaction. And more specifically, what Glenn suggested is that what models were lacking was the upscale energy transfer from the unresolved scales to the resolved scales in the model. And he suggested a way to simulate that using a so-called stochastic kinetic energy backscattered scheme. So Judith Berner joined the center to work with us and actually implemented a scheme similar to what Glenn developed at the Met Office at the European Center model, and working with Martin Leutbecker and Martin Steinhammer and other colleagues of us at the European Center, they put in the system also a new type of stochastic perturbations in the right-hand side of the equation, which was based on this backscatter idea. So try to feed back into the scales resolved the models energy, upscale energy that would have been simulated if the model had a higher resolution. What about the seasonal and climate ensembles? So what I've shown you so far was the path that we followed in trying to improve the reliability of our medium range, monthly, and seasonal system. What about the longer term range? Well, on the seasonal time scales and beyond, there is another couple of approaches which are followed to try to make the ensembles more reliable. The first one is a lagged approach. This is very old ideas which were actually developed by Eugenia Calnet and colleagues in the States in the 80s, and was also tried at Met Office and the European Center later on, try to combine forecasts starting at different times, emerging members with lagged start dates. This approach doesn't really work for the medium range because the lagging makes some forecasts much better than others, so you cannot really mix them in a good way. But if you go beyond a couple of weeks, then mixing lagged members could start showing positive impact. And the second approach that people were followed is a multimodal ensemble. Now, Canada, when they implemented their first ensemble, used actually a multimodal approach where we're using two dynamical cores and different parameterized parameterization schemes. But they immediately realized that it was very difficult to maintain two models with all these different schemes, so we went back to a single model, only single dynamical core. But in decadal and IPCC projection, clearly the way which is with one estimate, which makes more reliable projection, is to use a multimodal approach. Okay, so I'm reaching my last point of the talk. How can we make further progress? How can we keep improving the system? First of all, let me say that I believe that there is still a room for improvement in the medium range, in the monthly, seasonal time scales, and beyond. In the medium range, for example, forecasts today are very, very reliable and very good if you look at the synoptic scales. If you look even at grid point values, but far from the surface. If you start looking at surface variables like precipitation and 2-meter temperature, then the reliability is not as great as it is for example, the flow at 5,000 meters, or the temperature at 850 hectopascal. So more should be done and can be done, I think, to further improve the reliability of the ensembles if you focus on the fast scales and the smaller scales. Second point, by reducing model drifts, by reducing model biases or flow-dependent biases, we can, I think, further extend the forecast range of skillful prediction. So there is room for further improvements. How could we do it? Well, I think I will mention two areas of ongoing development. The first one is the convergence of NWP and climate approaches, which is clearly helping to develop systems and make them better. Why is it the case? Because if you use the same type of model, the same approach, the same similar resolution for climate projections, decadal, and the seasonal, subseasonal, and medium range forecast, you can test the same model on different time scales and learn from the different time scales. For example, if you have at the European Center, when we were testing our model over longer time range, we were realizing that the model was drifting. It was drifting because we had some problems with the radiation scheme. which one was fixed. And in this way, we could improve not only the longer range, seasonal and annual forecast, but also the medium range. And similar examples could probably be done if you think about climate projection. So indeed, if you think about what was done in the 1990s, when NWP was done mainly with atmosphere, land surface, models simulating only atmosphere, land surface processes, and IPCC was starting to use also coupled system with dynamical ocean and sea ice. Today, we have reached a situation where the models have a lot more commonalities, despite the fact that, okay, in NWP, we're still lacking some processes which are essential to be simulated if you want to do climate projection. But also, if you think about the approaches that are used, which are ensembles for both, we are much more similar. Not only that, models which are developed for medium range, monthly and season are also used for IPCC projection. Think about the unified model used at the UK Met Office and the Hadley Center for IPCC projection, or the ECMWF model used for forecast by the European Center and used by the EC Earth Consortium to make a climate projection. Second point that I want to make is the definition of better and more accurate initial conditions by using coupled data simulation system. A European Center developed and was the first one to produce a coupled reanalysis of a 20th century from 1900 to 2010 within the Year Climate 2 project. That same system is under testing to be used operationally to generate initial conditions for the ECMWF system, and it can also be used to estimate in a better way climate states, the past climate states. So again, this is a second point where by working together, scientists working on the two different time scales can make further progress. Let me conclude by saying, if you want to estimate uncertainty, an ensemble is better than one, even if it's a spatial one. So I think we need to keep focusing on ensembles, on ensemble of Earth system models, which is a point I will discuss in my lecture tomorrow at MISU, the Department of Meteorology, where I will focus more on Earth system models. And I conclude here, thanking again the Bolin Center for having invited me. I hope you enjoyed my talk. I'm happy to take questions, and I thank you very much for listening. I'll stop sharing my screen and I pass the control back to the Bolin Center.
All right. Thank you very much, Professor Roberto Buizza, for this very informative talk. So at this point, we invite questions from the attendees. And you can either write your question in the questions and answers little toolbox, which you will find down in your tools downstairs in your web browser, or you can also decide to raise your hand. And if you do that, we can give you audio so you can ask a question verbally. We do have one question already from Roxana Kremer. And perhaps we can start with that one. Is that okay, Roberto?
Yes, I can read that. So how much do you think is the less flying at the moment affecting the prediction? How important are the airplane data, especially looking on the data collected over the oceans? Okay, so airplane data are quite important, actually. They are quite accurate, more accurate than, for example, data from a satellite. Very small number compared to the data coming from satellites. So you should not expect them to have a major impact on weather prediction, but they do have an impact. Indeed, you can find, so when I say they have an impact, I would probably say the fact that there are less aircraft flying, so less data, say, from aircraft, have increased error by maybe 0.5 to 1%. I don't think it's a value bigger than that. There are studies done by a different center. For example, European Center has done it, where they actually estimate the impact of a different observations coming from different platforms on the skill of forecast. And I invite you to go and look at these papers for more precise data, more precise numbers of what is the value and the impact of aircraft data on forecast. I mentioned to you a couple of names. So one is Tony McNally, and the other one is Carla Cardinali. So if you look on the ECMWF website and search for Technical Memoranda by these two authors, you should be able to find more precise answer to this question. So thank you. So I see a second question from Gabriele Messori of Uppsala University, who says, I was puzzled by the fact that in the initial example, the cyclone track from a high resolution member seemed to be outside the ensemble range. Was that indeed the case? Okay, clearly, yeah, that was the case. And point number two, since that was generated using a high resolution model, you wouldn't expect it to be inside the ensemble spread. Also because when forecast probabilities are computed at the European Center, they are computed, in this case, the strike probability using only information from the ensemble. So the high resolution is a bit of a different beast in the sense that it has 2 times higher resolution, 2 times more scales resolved, different characteristics. So you should not expect it to be inside because of this. Clearly, one could design products in a different way. And in fact, there are, in some other products of European Center, the high resolution model is included, and other users actually include them. So, but the fact that they were not, the high res was not included in the strike probability map is why you wouldn't, you have seen it as outside the range of the ensemble strike probability. I can see, yeah. Shall I go ahead, Annika?
Yeah, I think perhaps we could give the word to Tom Nicholas, who has raised his hand, and he can ask his questions verbally.
Okay.
Tom, I'm going to go ahead and give you permission to talk. So welcome to ask your questions. Tom, are you with us?
Hi, can you hear me?
Yes.
Yeah. Sorry. I was just wondering how many of these uncertainty techniques are transferable to climate models. So, for example, you talked about multi-model prediction is obviously something that can be applied in both cases. But given that one's an initial value problem and one's a boundary value problem, are there limitations to what other methods can be transferred across the two questions?
Yeah, good question. So I think there are clearly some limitation. I mean, you said that the climate project is mainly a boundary condition problem. I might want to challenge that in the sense that if I think about the slowly evolving components of your system, I'm thinking about the ocean, for example, having a correct initialization of the ocean might matter for 10, maybe 20 years forecast, maybe not for 50 to 100 year projections. But clearly, I would probably argue that in the decadal time range and possibly up to 20, maybe 30 years, it might matter that you have an ocean which is well initialized, especially with well and good initialized undercurrents. So if you think about that, you can imagine that having a good method to sample and design initial perturbation of your ocean state could be important. Model error schemes, I think, could be and should be included in IPCC projections. Perturbations of these RCPs also, which is what they do. So there are some aspects which could be translated also. Probably not singular vectors, since you need to be able to work in the linear regime to use them. So back to Annika, do you want to give a floor to someone else, or should we take
I think perhaps we can end with one final question, and then time is running out. So we don't have any raised hands at the moment, so feel free to choose.
Okay, so one anonymous attendee asked whether the seminar will be available on the internet, and the answer is yes. Annika, I think the Bolin group will put them on. I'm happy for that to be. I don't know exactly where, but if you write back to the organizer, they will send you a link. Then I have a question about communicate uncertainty, which I think is quite interesting. How do you communicate uncertainty to the users and general public? What's your experience in this sense? So I will talk a bit about this in my Bolin lecture, because I think it's a very important aspect. I would say that we need to communicate it, and actually I think users are actually not so ignorant about uncertainty. A lot of members of the public play games which are inherently probabilistic, and they can perfectly understand the chances to win or lose if they play roulette or whatever. So I think I would try to clearly use simple language, but I suggest that we should use more forecast. For example, we should show more at the forecast the fact that if we talk about predictions for next week or next month, there is uncertainty, and I would show how uncertain are our forecast. This is done sometimes by some presenters. I have in mind BBC presenters using them, and also I've seen the colleagues from Sweden. Colleagues from Sweden showed me that in their newspapers, in your newspapers in Sweden, some images are shown where uncertainty is also shown up. So I think there are ways to communicate uncertainty also to the public, and I certainly would favor that. So I think, Annika, do we need to stop? Because if you want, I can take another question.
Well, perhaps we should try and keep the time. So I will give the floor back to Nina.
Okay.
Yes. So, Roberto, thank you so much for this really interesting science seminar. I would also like to thank all the participants. We had more than 130 people that had zoomed in and followed this lecture, which is really, really nice. And I would also like to thank Annika Granebeck and Laila Islamovic, who have been doing everything behind the scene to ensure that this runs smoothly. Finally, I want to invite you to join us again at 1 o'clock for the Bert Bolin climate lecture that Roberto will give. 1 o'clock, and there is another Zoom link, and hope to see you there. Thank you so much.